So last time we were talking about, we introduced the per unit system last time, and we did an example and saw that with the per unit system you sort of create a one-to-one transforming. Specifically, if we're talking about the transformer, from a transformer's perspective, what the per unit system does is sort of create a one-to-one transformer. If you have a one-to-one transformer, it means that the voltage times the current at the input is equal to the voltage times the current at the output, right? And if it's a one-to-one transformer, then the voltages are equal, which means that the currents are equal, right? So we said that we can represent the ideal transformer in per unit system as nothing but a short circuit, right? You have the primary voltage, secondary voltage, they are equal. Primary current, secondary current, they're equal, only in per unit, right? And then we went through an example where we had an impedance in the impedance of the transformer, the series impedance of the transformer was given, right? And we went through that example and we saw that, okay, when we look through the primary, the impedance is the same as looking through the secondary. So we looked from this side, and we were able to measure, we apply some voltage, a certain current will flow. Let's say you put a short circuit, for example, and you have a black box, like the Thevenin equivalent circuit, right? So or a two-port network, right? You put voltage on one side and look at the current. It will tell you what the equivalent impedance is in this box, right? Same thing with the transformer when we look from the other terminal, right? So from both terminals, the impedance was the same, right? So we concluded that we can represent that, we can model that as a series impedance in line with our, two terminals. So now these become the terminal voltages, not the back EMF voltages, right? E is the voltage developed at the winding itself, right? At the winding, not the terminals, right? If you want to include the effect of the series resistance and the leakage flux, then we have to put this series impedance in place, right? So typically in power system analysis, from our perspective, when we're modeling a power system to understand, how the city will expand, or what kind of new equipment we need to put, or what the rating of equipment we need to put, which is the focus of this course really, and we're gonna push very hard on that in chapter 6. Then we will typically utilize this model of the transformer, just a series impedance model of the transformer, because this is really what affects voltage profile, right? Voltage drop will be because of the fact that we have an impedance in series, right? So this is really a big something. It's a big parameter in the design of the power system components that we will in a power system that we will be designing it. So per unit allows us to do something like this, right? Insert this in series. We will typically just forget about this shunt branch completely, right? That we studied it because we need to. It exists. Excitation current exists. We need to know how to extract these parameters and test these transformers, etc., etc. And it's important for other aspects of the power system. Other detailed aspects like protection of the transformer itself will require you to understand this, of course, right? But if I'm looking at a larger picture of the power system, I will just represent it as a series impedance, right? So that's the difference between these two representations of transformers. And this is just in per unit, guys, right? If it's not per unit, the transformer stays there, right? If we did not convert or normalize everything using the per unit system, then the transformer stays there, right? Which is a bit of a pain for us to analyze, right? And we don't even know how to do it for a star-delta transformer yet, right? So for a star-star or a delta-delta transformer where the voltage in the primary and the voltage in secondary and series are in phase, it's easy. That's the case we studied. Today we will study the other case where we have a star-delta type transformer. So any questions on what we did last time and the conclusion from what we did last time? On the idea of the per unit system and how it applies to a transformer. We'll do a lot of examples, yeah, but I just want to make sure at least the reasoning behind it is understood, yeah. And the great motivation, one of the quick outcomes that we saw was this. Okay. So in the example that we studied, if we go back and read the example, they were telling you to use a transformer rated values as base. So if we go back to the example, right, that you said using the transformer ratings as base values, right? So we remember we said that these base values are a choice, right? You do not have a right answer or wrong answer, right? We said that around the transformer there's something that makes sense, that the ratio of the voltage bases is equal to the ratio of the transformer voltages, right? If the ratio of the voltage bases is equal to the ratio of the transformer voltages, right, then we end up with this one-to-one transformer. One-to-one transformer, which we can eliminate and just put a pure nothing but a short circuit, right? So that was the reasoning here. But what if I have many different types of transformers, and what if I'm changing the taps on transformers, and what if I have different generators with different operating voltages around the system, right? So how do you choose a base, right? Or how do you build your single phase equivalent circuit in this case, right? So obviously when we looked at you remember when we looked at the data sheet or the nameplate for the transformer, the impedance was given as a percentage, right? If you go back all the way to the beginning, the impedance here of this transformer here, it was given as a percentage, right? So this was the transformer impedance right here, 8.17%, meaning 0.0817 per unit, right? So that's the per unit and percent are basically interchangeable, right? So the impedance was given as a percentage. Remember the value of the definition of per unit is what? Z per unit is equal to Z actual value over the base, right? So, and this impedance, they're giving it to you as a per unit. On what base? On what base?
How did we know that it's going?
It's a percentage. They don't give it to you in ohms. They give it to you here, percentage or per unit, right? You take this divided by 100%. That's your per unit value. So they gave you the impedance. They don't give you the impedance as an impedance, an actual value. They will give it to you in per unit all the time. On what base, guys? Come on. What makes sense? What makes sense? Current of what? But this transformer is not operating now. They're giving you an impedance without the transformer in per unit, without even operating the thing. So the base is what? Does it make sense for the base to be the rated values of the transformer? Right? It makes sense, right? The transformer is a certain value. You know, this is a 14.4 kilovolt to 8.3 kilovolt transformer, right? So you have the voltage ratings of the windings, and you have the power rating of the transformer, right? So you have the power base, and you have the voltage base. So from the power base and voltage base, we can calculate the impedance base and current base. So that's it, you're done. You have the if you have two of the base quantities, we can calculate the other two, right? So you have two of the base quantities, you can calculate the other two. So typically equipment parameters, equipment data sheets will give you AC power equipment data sheets will give you impedances in per unit, and they will be based on equipment ratings, right? So this transformer is rated for a certain power, certain voltage, means certain current, means it will have a certain impedance base. Okay, then this impedance that they give you in percentage per unit is based on that transformer's base values, right? And that using the ratings as the base values. Okay, how about if you take this transformer and stick it into a system? I stick it into a system where this is the low voltage side is 8.3 kilovolts. Here it's 14.4 kilovolts. How about if this is connected to a generator that is generating at 12 kilovolts? The generator's data will be given on what base? The generator will also be given. You will be given the impedance of the generator, right? On what base? Exactly, on the generator's rated base. So now it's a bit confusing, because now I have a generator and I have a transformer. I got impedance of this transformer using its base. I got the impedance in per unit using its own base. And I got the impedance of this generator using its own base. But what did we say? We said that, every transformer I will change the base voltage. Right? We said last time that we will unify the power base. We'll use the same unified power base for the whole power system, right? And we will choose a voltage base that we will change every single time we see a transformer winding, right? But this impedance was given on the generator's voltage, which was in this case 13 kilovolts, and this one was 14.4 kilovolts to 8.3 kilovolts. Right? So what do? The bases are different, right? Here the base is maybe 14.4, and here the base is 8.3, for example. That's what this impedance was calculated at. So what do? There has to be a way to do a change of base, right? Sort of normalize everything to the big power system, right? So I have something normalized to itself. I sort of need to re-normalize it so that I can put it in a big power system. I have something else that's normalized on its own ratings. I sort of have to do some manipulations to put it back into this power system that I've normalized at a certain base value, using a certain base value, right? So every equipment you will have to look at its parameters. If they're given in per unit, it's using its own base or own ratings as base values. Okay, so it's using the machines or the equipment's ratings as base values. I bring in equipment rated for different values now into the system, right? This is a what? This is a 24 megavolt ampere transformer, right? Rated. This is its rated power. This is the S base that I've used for the transformer. The S base here is what? This is a 50 MVA generator. Completely different power base. Right? Completely different power base, completely different voltage rating, completely different power base, completely different voltage rating. So everything is different. So I cannot do that. Right? So I will have to find a way to change bases. It's almost like, okay, I will go back to calculating actual values. It makes sense. You can go back and calculate actual values, right? If you have all the bases, right? If you have the bases, right? If you have the base value for impedance, and you have the per unit value for impedance, can you go back and calculate actual values? Yes, you can. So it's like having to go back and calculate actual values and then calculate the per unit values on a new base. Okay? Why do we do that? I don't know. Why don't they just give us impedance as a real value? This is just power system. Power system people like to speak in normalized fashions. They know 0 to 1. Everything beyond 1 they don't like. Everything below 1 they also don't like. They like to operate around 1. So I don't know the reason. Why don't they just give you actual values? Okay, so that is what we will talk a little bit about. It's called change of base. Because before we do that, I cannot build a big system anymore, right? We did an example where we had a specific piece of equipment, and we looked at this specific piece of equipment and converted its impedance to per unit, right? But I cannot now build a larger system without having multiple pieces of equipment, and these multiple pieces of equipment I need to bring into one system. And we said that system has to have a unified power base. Right? If we're going to normalize the system, it will have a unified power base. So this is the reason behind what is called change of base, okay, or changing from old base to new base values. Okay, this is why we do that. Yeah. So as we just discussed, when only one component, such as a transformer, is considered, the nameplate ratings of that component are selected as base values. And that's why we can easily eliminate the turns ratio and just plug it there and play with the transformer itself. I bring in other equipment with the transformer, does not work. I cannot use the same base values anymore because other equipment are The values are provided on the rated. The base values are provided on the equipment's rating. So I have to do a change of base. What does this mean? It means the new base value is equal to what? It's equal to the actual value, of course. The definition of per unit will not change. The per unit will be actual value over base value. But which base value? A new base value now. Right? A new base value different than the equipment's rated bases, the equipment's rated base values. Okay, so basically it's like as I said, it's like converting the old per unit value to actual and then converting to a new using a new base value, right? Then this is what this is. So if you have your old per unit value, right? So let's remember Z per unit is equal to Z actual over Z base. This Z base was old, right? This is Z base old. So Z base old multiplied by Z per unit old is what? Actual value, right? So I converted, so this is Z per unit old multiplied by Z base old. These two multiplied by each other is basically the actual value. I take this actual value and divide it by my new base value. So it's the same definition. I just convert it to actual and then convert it back to per unit again. Okay? And then all the previous definitions of, again, this is my Z base, my new per unit value per unit value for impedance. Again, everything that we discussed before applies as well. So all the equations for active and reactive power, etc., for base quantities apply. So here I can rewrite this as what? Z per unit new is equal to Z per unit old, which is this, right? And then they rewrote Z base old over Z base new. If you go back to the definition of Z base, Z is equal to what? V base squared, right? Z is equal to V base squared divided by the voltage, right? Or by the power. Is it? So S is equal to V times I and
V squared over R.
And it's equal to V squared over R. No. Where did we get this from? Huh?
Z is V squared over S.
S over V here.
It's V squared over S.
What's V squared over S? Sorry.
Z.
How did you do that? You substituted?
It's S is V squared over Z, right?
Yeah. So it's just the substitute.
V equals I times Z. So Z equals V over I.
Mm-hmm.
So I is equal to what? V over Z?
Yeah.
V over Z. Right? So V squared, exactly. So V squared over S is equal to Z. So that's what we have here. I'm just rewriting this Z base old as in terms of V squared over Z. Base values, right? So it's V base old squared over S base old. And then Z base new is V base new squared over S base new. Okay? So, as we said, we will be typically given the equipment's rated values for each type of piece of equipment. Then, all of these equipment, we will put them into one system to operate together. This one system, we want to analyze it and build a single-phase equivalent circuit in per unit. For us to do that, we have to either convert back to all the actual values and do the and then use the new base values, which are common to the full system now, right? So originally the base value was the equipment's rating. Now I want to come up with base values that are unified for the full system, right? So this is what we need to do. Just an application of this equation. So let's look at, I think an example comes next. Yeah, an example comes next. So we have 3 zones of a single-phase circuit are identified in figure 310. I'll show you what 3 zones mean. Okay, the zones are connected by transformers T1 and T2, whose ratings are shown. Using base values of 30 kVA and 240 volts in zone 1. So here, again, choice of base value is a choice. There's nothing wrong with it. So most of the time, to help you solve the problems, we will help you choose the proper base in a certain zone. And then, if you your choice of base on the other zones is up to you, right? If you choose the base in a different zone such that intelligently, then you will be able to eliminate transformers, right? So here, let's look at the 3-zone circuit that they're talking about. So this is a 3-zone circuit they're talking about, right? So I have a generator, right? And then a transmission line, generator, a transformer, a transmission line, a transformer, and a load, right? So this is, they divided it. Anytime you see a transformer, put a line. Anytime you see a transformer, so put a line. Because what did we say? We said that the transformer changes the voltage in the system. So we will have a voltage base on the right side different than a voltage base on the left side. A good choice of voltage base around the transformer is one where the ratio of the transformer terminal voltage is equal to the ratio of the bases that you've chosen on both sides. Meaning, if this is a 240 volt to 480 volt transformer, a good choice of voltage base would be 240 on the primary side and 480 on the secondary side. Right? A good choice would allow you to do what? Eliminate this transformer and make it a one-to-one transformer. Right? If you chose the voltage base to be equal to 240 on the primary side and 480 volt on the secondary side, then this transformer will look like a one-to-one transformer, because you will take the actual value divided by the base, which in this case will allow this transformer to look like a one-to-one transformer, and you can represent it as nothing but a short circuit. Of course, if it has impedance, you have to put this impedance in series, right? But there's nothing wrong with choosing a base of 240 on the primary and a base of 500 on the secondary. There's nothing wrong with that, right? There's nothing wrong with that. But in that case, you cannot eliminate the transformer. You will not be able to eliminate. You don't have a one-to-one transformer. You will have a 1 to 1.1, for example, transformer, right? So you did nothing, right? But it's not wrong. You can still solve the problem that way. It's your call, right? So let's see. So let's see if you make the right choices, how easy it becomes. And then we will, I think later in the class, we will solve one with the transformer still in there. Okay, so we have these two transformers, and they're telling us in zone 1, choose 30 kVA and 240 volts as the basis, as the power base. Does the power base change in the system? When we come to analyze the system and normalize it, the power base is the same. It is the same all over the system. And then they tell you to choose 240 volts in zone 1 as the voltage base. Then they ask you to draw the per unit circuit and determine the per unit impedances and per unit source voltage. Then calculate the load current both in per unit and actual values or amperes. Transformer winding resistances and shunt admittance branches are neglected, right? So all the shunt branches are neglected, and they say that the resistances of the transformers are also neglected, right? We said that we'll typically do that. Actually, we'll typically represent the transformer just as an inductance, series inductance. Yeah. Okay, so let's see how we solve that. Okay, so you see a transformer, put a line. See a transformer, put a line. Okay, and then the way I would like to see. Okay, then I would recommend put all the rated values of the equipment that you have. So this is a transformer that is 30 kVA, 240 to 480 volts, with an equivalent impedance of 0.1 per unit. So that, this is the series impedance of this transformer, given as a per unit value. On what base? The transformer's rated base values. Right? So the transformer's ratings were used as base value. So this is a 240 to 480 volt transformer. I used base on the primary as 240, base on secondary as 480, same as the transformer's ratings, right? So I would recommend doing this, right? Write all the givens, write the ratings of the equipment. The load, I guess, is a given. Did they give us the load? Yeah, I guess they give. They didn't write it up in the storyboard, but basically. So you're given a load in actual values, right? This is an impedance in actual values. So they mix things up, right? So they give you an impedance in actual values for this. And then they gave you a line impedance, 2W, I think this is 2 ohms, sorry. X9. Yeah, it has to be, this is ohm, this is not W, sorry. This is ohms.
The Z load is,
Huh?
Z load is,
Z load is in, this, yeah. So it looks like they messed up the ohm and W, sorry. Okay, so that this W is ohms, sorry. Okay. Right, so this is ohms. So this is actual values, right? This is actual value, right? This is 220 volts, 0 degrees, that's what it looks like, right? And then this is the transformer ratings, power rating, voltage ratings, and then per unit value on transformer's base, using a transformer's base ratings as base quantities, okay? Using transformer's rating as base quantity. Same thing here. Now I would like to draw the per unit equivalent. Put all of these equipment, this generator, transformer, transmission line, transformer, and load are in one system. I would like to now solve and figure out what the current is in the system, for example, right? So to do that, I need to build my single-phase equivalent circuit representation of this three-phase system. And I would like to use normalize everything using the per unit system because I don't want to deal with transformers. I want to eliminate the fact that I have transformers and just have a nice simple circuit that looks like my 214 type problems that I have. Okay, so how do I go about that? Let's do the easy stuff first. They told us to use a base on the primary side on zone 1. This was zone 1, right? They told us in zone 1 use 240 volts as your base voltage, and they said 30 kVA, S base is 30 kVA, right? This is what they told us. So this is nice because if I use 240 volt as my base quantity here, so V base 1 is 240 volts. If I use they told us to use 240 volt as my base here. What will be my base voltage on the secondary side of the transformer? The only thing they defined was base voltage in one zone, right? So now I would like to go and, as I said, come up with the base quantities in every zone, okay? Calculate the base quantities in every zone. Whether you need them or not, let's see. But they gave us the voltage base here. Now I would like to calculate the current. The power base is the same for the whole system. So I would need to calculate the current base and impedance base in the various zones. Yes?
Why is the power base the same in all systems?
Because there's the system will be rated for a certain value of power, right? So, for example, you run the system in Qatar, for example, in summers we're sort of consuming about 5 gigawatts, full system, right? So it makes sense that each one of these generators, I want to know what sort of proportion of that full power, for example, that each generator is providing and contributing to the system, right? So if I know that this generator is rated to 0.1 per unit, and I know that I chose my base such that it's sort of the average operating power of the full system, then I know how much contribution. Without going into the ratings of this specific piece of equipment, I would know what is the contribution of this generator, or how much this transformer is, how much power this transformer is. It's just a philosophical choice. Yeah, there's nothing wrong with it. Yeah, I mean, there's no right or wrong answer. Versus if you choose the base value, for example, the base value for power as the power rating of one of the generators, right? Then if you are operating the full system, the full system will be, if you want to calculate the power in the full system, and it's going to be 105 per unit, right? It's not very intuitive, right? And not helpful for you to understand what's happening in the system. Yes, sir.
yeah, what is the 20 kVA?
20 kVA. This is the rating of the other transformer. So this transformer has a rating of 20 kVA. This one has a rating of 30 kVA, right? So since this one has a rating of 30 kVA, and 30 kVA is the base power for the system that they told us to use, right? And this transformer also happens to have a voltage rating of 240 volts on the primary side. And they told us in zone 1 to use 240 volts as a base value, right? Then what is a good choice for base voltage in zone 2? 480 volts, right? Because we said that if you choose the ratio of the voltage bases, so V base 1 over V base 2, if you choose the ratio of the voltage bases to equal the ratio of the transformer voltages, transformer voltage on terminal 1 versus transformer voltage terminal 2. Then if you do this, if your choice of base, if the ratio of the bases is equal to the ratio of the transformer terminal voltages, then you should be able to eliminate the transformer because it's going to be a one-to-one transformer. Right? So this is helpful for you to eliminate the transformer. So a good way to choose, a good number to choose for base voltage on the secondary side would be 480 volts. If I chose it that way, then I've satisfied this. If I've satisfied this, I have a one-to-one transformer for this thing. And I can eliminate it and put its representation, which is nothing but a short circuit. Right? The ideal transformer portion of it, right? But they also told us this transformer has a 0.1 per unit impedance. On what base? Transformer's base. Transformer's base voltages and power happen to be equal to the same power base for the full system, and same voltage base on the primary for the full system, and same voltage base on the secondary for the system. Right? So because I chose the voltage base here to be 480. Right? It's the same voltage base as the transformer. The ratio of the bases, 240 over 480, is equal to the ratio of the transformer's terminal voltages. Right? So this is satisfied. So if this is satisfied, then basically it's equal, right? So for 240 is 240, 480 is 480. Then and the power base is the same. Then this impedance was calculated on this base, and this base is the same as the system base in this case, right? So I can just take this 0.1 and put it back here, use it in the equivalent circuit, right? But this transformer is different. This transformer, okay, at least the power base is different, right? The power base is different. Whether the ratio of the voltage bases will be equal to the ratio or of the bases that I will choose or not, we will see. But the power base is different. So obviously this 0.1 will need to change. Right? I will need to do a change of base for this one. Yes, sir.
So you said the transformer one is represented by the impedance, just that?
Yeah, all our transformers, we will convert them to, if you're given equivalent impedance, a series impedance for the transformer, it will be this is either a short circuit or a impedance in series. So the transformer is either going to be represented as a short circuit like this, pure, or as an impedance in series.
So you choose the same impedance as given because the ratio was the same? With
Exactly.
The
Because the power base is the same as the full system power base that I asked us to use. And the ratio of the voltage bases that I've chosen, which is 240 and 480, the ratio of the bases is equal to the ratio of the terminal voltages of the transformer. Since these two conditions are satisfied, then I don't need to recalculate this. Impedance here was calculated on the right base already. So there's no change of base required for this transformer. Okay? No?
If it was not
It's
the
not?
same base, if it was not the same base, how would we do it?
Exactly, that's what we'll do here. The other transformer is not the same base. The other transformer, the power base, this is the power rate. The power rating here is 20 kVA. This 0.1 per unit was calculated on the base. The bases being used were the ratings of the transformer, which was 20 kVA and 460 over 115. Okay, so let's see how we will deal with it. So, but is this one understood? At least this one we will just bring down here. We don't need to do anything about it. So we put our line here at the transformer, and then we calculated the voltage base here. We calculated the voltage base here. Now let's calculate the voltage base here. Okay, we'd like to see how they came up with this 120, right? Because this transformer is 460 to 115, right? And my base here was 480, right? So how can I eliminate this transformer? We said I can eliminate it if I chose my ratio of the voltage bases. So 480 to some V base in zone 3 is equal to 460 over 115. So what is that? 480 times 115 divided by 460. It's 120, right? Calculate it so you can trust me. It's 120, right? So I chose V base here to be 120, and you did the calculation. I didn't do the math, right? So we chose V base here to be 120. Since I've chosen V base in the zone 3 such that the ratio of the base values is equal to the ratio of the transformer terminal voltages, then this transformer will also be a one-to-one transformer. Okay, so that's done. And now I need to look at its impedance. Its impedance was calculated on which base values? A certain power base and a certain voltage base. The power base and voltage bases are different than what I've chosen in my system. So I have to do a change of base for this impedance. So this impedance will change values. And we'll apply the equation that we just saw before. Right? So this impedance will change its value. So this is not 0.1, it's going to be 0.137, blah, blah, blah. Right? We'll look at the math for this right now. But I have my S base new now is 30. This is S base new for this transformer. S base old is this 20 kVA. Right? V base on the primary side old is 460. V base on the primary side old is 480. V base on the secondary side is 115 and 120, right? So we will just use our old quantity. These will be the old quantities in the equation that we just introduced. These will be our old quantities, and our new quantities will be the new S base for the full system and the base voltages that we chose in our in the different zones. Okay, so that's why this impedance changes. Now we have to deal with this one and this one. These were given as real values, so 2 ohms, and then 0.9 plus J, blah, blah, blah. So these are given as actual values. So for you to find the per unit values, I have to do what? So per unit is equal to actual over base. So I have to definitely find the base impedance in this zone, and I have to find the base impedance in this zone, so I can take my actual values and divide them by the base values in this zone, right? Now let's go back. Let's see how. That's why I say, okay, put the lines whenever you see a transformer, and then calculate the base values in all the zones. You start with. Sometimes you will typically be given the base value in a certain zone for voltage, so that we can sort of have a similar numbers, okay? And then work your way through the system to select the bases for voltages in the different zone. You have the base for power. Then you go back to the equations for base values that we went through before, and come up with your base impedance and base current if you need it. You will need the base current in certain places because for example, here, remember, if this is a per unit circuit for the system, if we calculate the load current here, it's going to be load current in per unit. If I tell you, then they tell you they want the actual value or the load current in amperes. What does that mean? I need to take my load current, which I calculated in per unit, multiply it by the base current where? In this zone. Remember, the base current will change in each zone because the base voltage change in each zone. Right? That's why divide the circuit up in zones, calculate your base quantities, and then solve your circuit, and then deal with the problems. Okay? The guy would be me in this case, right? Okay, I calculate the generator current, calculate the load current, and that's all I can do, right? It's not complicated really. Power systems is very systematic, yeah. So So here, the selected base voltages, calculated base impedance. Again, sorry about the W versus the ohms. I did not see that. Seems like it's everywhere. So, and then calculated base currents, right? So in the various zones, right? So let's see what how the problem goes. So, as we said, 30 kVA will be the common base for the system. 240 volts will be the voltage base in zone 1. Then I go to zone 2. For me to choose a base in zone 2, a good choice of base will maintain the ratio of the bases. So since the base voltage in the zone 1 was given here as 240 volts. So what I'm missing is the base voltage in the second zone. So V base 2, which is the second zone, divided by 240 volts is equal to the ratio of the transformer voltage ratings. So I was able to calculate the base in the second zone. And then I go to the third zone. I use the same. I use the transformer terminal voltages ratio and come up with the base voltage in zone 3 so that I can make sure that the ratio of the base voltages that I chose in a different zone is equal to the ratio of the transformer terminal voltages. Right? From that I calculated the 120 volts as the base voltage in zone 3. Then go and calculate your impedance bases in the different zones. And then if you need, calculate the current bases in the different zones. Right? So that's what we did here. So the impedance base in zone 2 is V base zone 2 squared over S base. S base is common. It's always 30 kVA. Always 30 kVA. But the difference here is the two bases, the two base voltages, right? So I calculated the base impedances in the two zones. And then they asked us for the current, the load current in amps, for example, right? So for you to do that, you have to calculate the base current in where the load, in the zone where the load is connected. So I calculated base, S equals V times I, right? In zone 3, I base 3 is equal to S base over V base 3. S base over V base 3, right? So now I've just jotted down all the bases in the different zones. After that, you have to start converting your impedances, looking at your impedances and building your circuit. To look at your impedances, this is the logic is what we went through before, right? So since S base is the same for the transformer T1, right? So since the S base for the system is the same as the rating of transformer 1, and V base in zone 1 is 240 volt, which is the same as the voltage rating of the zone 1 side of transformer 1, which is the logic we talked about, the per unit leakage impedance of transformer 1 is the same as its nameplate value, which is 0.1 per unit. Okay? We went through this. We just write it down here so that you can remember it. Okay? And then, however, the per unit leakage impedance of transformer T2 must be converted from its nameplate rating to the system base, right? Because remember, the power base was different for the transformer. The rating of the transformer was different than the system base that we chose, right? So we have to do the change of base. So we go back to the change of base equation. It says what? It says Z per unit new is equal to Z per unit old, ratio of the powers, ratio of the voltages, squared. Okay? So we are given our old per unit impedance, which is 0.1, Z per unit old, ratio of the voltages, ratio of the powers. Okay, old voltages in the system that you chose to calculate the impedance on, and then the old power base and new power base. Okay, so it just this equation is nothing but this equation up here. Exact same. Okay, so now you apply this to anything that needs to be applied for, right? So extra, and you can do this. Does it matter? Remember, this is in per unit. So the impedance of a transformer, if you look at it from the primary, is the same as the impedance of the transformer if you look at it from the secondary, right? So here we use the voltage ratings to be on the primary side, 480 and 460, right? Or you can use 115 and 120. Does not matter. The impedance in per unit will be the same, looking from the primary or looking from the secondary. because you chose the ratio of the base values to equal the ratio of the transformer terminal voltages. Because of that choice, this doesn't change. The impedance will not change. So because of that choice. Okay? And then the transmission line impedance was given an actual value. So you have to calculate, you already calculated the base value of impedance in zone 2 where the transmission line is located. You take the actual value, which is 2 ohms, divided by the base value. Base value was the base value in zone 2. The transmission line is in zone 2. Right? It's in zone 2. So you calculated the base impedance in zone 2, which was 7.68 ohms. Right? So you just take the actual value divided by the base value of impedance in that specific zone. Right? So that's 0.2604. Right? And we do the same for the load impedance. Exact same. So we divided the actual value by the base value in zone 3 as well. And we came up again. Remember, base values are a single number. They're not a complex number. It's not a magnitude and an angle, right? It's always a fixed number. But per unit isn't. Per unit is an actual rectangular value. It has a real and imaginary component. After this, what have you done? Now I've built my circuit. Now I've built this circuit. Can you solve this circuit or not? This is something you can solve. This is, I mean, if you're given, are you given the voltage value? I don't know if you're given the voltage. Yeah, you're given the value of voltage, 220 volts, angle 0. Right? So in per unit, what is the value of the voltage of the generator? What's the value of the voltage of the generator? Actual over base. Actual is 220, base is 240, so it's going to be 0.9 something, right? So it's 0.9 something, but the angle doesn't change, right? Still 0 degrees. So I have a voltage source of 0.9 angle 0. I have all my impedances. Now it's a simple circuit, very simple circuit. Just voltage divided by the impedances is equal to the current. And now they ask you to go back and, okay, I want the actual value of current. Right? Now you want to go into detail. Right now you're not you're a system planning engineer that's sitting in front of this big power system, doesn't care about too much detail as long as everything is fine. Everything is fine, all the numbers are close to 1, everybody's happy, no problem. But I would like to get into details and design the protection system of a certain piece of equipment. I want to know why is this equipment failing or whatever. Now I have to get into details. To do that, I have to look at actual values again, right? So for me to assess what's happening at the load side, they're asking us, okay, what is the actual load current? Actual value, not per unit. So I have everything in per unit. So to go back to actual, I just multiply by the base in that specific zone. So I calculated the current. This load current in per unit is the same from out of the generator, the same out in the transmission line, and the same in the load. But actually, it's not the same. You have to multiply by the base value in that zone to find the actual value in that piece of equipment. Right? So if you want to calculate the actual current in the load, you would calculate so this is first the per unit current, so it's the voltage divided by the sum of the impedances. And then if you want to find the actual load current, you have to take your per unit current that you just calculated, multiply by the base current in zone 3, because that's where that load is located. Okay? And that's it, you're done with this example. Does it make sense? So it helps simplify the circuit. I mean, this per unit system helps you simplify, remove all the transformers. And this example was in single phase, but of course, most of ours, you were given voltages as 240 and 480. You were not given a three-phase system where we will start confusing you by the root 3s and the phase shifts, right? Phase shifts we will not when we add the delta transformers, but actually, there will be some phase shifts as well here. If you're given line voltages, you're constructing the single-phase equivalent circuits, right? Remember, in a three-phase system, the same thing applies. Per unit applies the same way in three-phase. The power base will be the same, but the power base will be typically given on the equipment rating as well, right? You were given a transformer rating of 20 kVA or 30 kVA. That's for that whole transformer. It happened to be single phase before, right? But now if you're given a three-phase power system and you're told the power base is 30 kVA, this 30 kVA is for that three-phase transformer, right? It's for the full three-phase system, yeah. And the voltage base in a zone, you're asked to select 240 in the previous example. Here you will also be given voltage rating of equipment. The voltage base will typically be the line-to-line voltage base, right? So it's the line-to-line values that we will always be dealing with, right? Terminal values. The line-to-line values that we see is going to be the voltage base for a three-phase system, right? So, but you can convert a three-phase system to single-phase. That's fine. You can operate in, instead of using the single-phase quantities, you can use three-phase quantities. In that case, instead of power is equal to square root of 3 V line times I line, and power is going to be equal to 3 V phase times I phase, right? So you just have to pay attention to the square root of 3 and 3 and 30 degrees when we do this. And we'll go through examples here. So, same as before, nameplate per unit equipment impedances are given on base values. So are given on bases defined by the ratings of the equipment. So same thing, three-phase equipment will be given, you will be given impedances based on the equipment's rating, right? So everything will be given in per unit based on the specific equipment's rating. So you have to still also convert it to the same base for the full system. So the process is the same. We have a power base that's the same for the full system, and we will choose a voltage base in a certain place, and then every transformer select a new voltage base, right? It's just a little bit more confusing because of the three-phase versus single-phase use. Yeah. The equations are, you've known. The equation for base quantities are what you've seen before. S base is equal to square root of 3 V line to line base multiplied by the base current, right? So power base is square root of 3 V times I. This is if you're given power in megavolt ampere, you just substitute, and voltage in kilovolt, you substitute in this equation. Yeah. So again, you will be given power base and select and recommended to use voltage base in as a certain value in a certain zone, and then you will have to calculate the current base and impedance base in the different zones. Same process for three-phase. Just the equations are there for you to help you go through this. And same the power. Again, if you have a piece of equipment with a certain impedance, you put it in a system with a different power base or a different voltage base, then you have to do this new base conversion. You apply this base conversion equation to calculate the new per unit value of impedance. Yeah. So I think it's better to look at the one thing to note. Yeah, one thing to note here. Power in three-phase is equal to what? Power in per unit is equal to actual power divided by the base power, right? So actual power in the three-phase system is equal to 3 V times I. The base power is also equal to 3 V times I. So one thing to note is that the 3's will cancel, right? So that's why it's a bit more confusing, because now you don't see, it's a three-phase system, but you don't see the number 3 anymore when you're calculating the per unit power, right? The per unit power does not have the 3 anymore, right? The actual values have 3. Right, the actual power, actual power is 3 times the voltage times the current, 3 times the phase voltage times the load current, or the line or load current. Since we're all only talking about star connections here, and the base is the same, but the 3's will cancel, and the per unit power will not have this. Right, so if you're going to go back to actual, make sure you take note of that. And we will only have S base. We will not have a P actual. So we will not have a real power base and a reactive power base. We will just have a apparent power base. So that's apparent power base will be used to calculate the real power per unit, and reactive power per unit as well. Okay, and the same thing applies. This 3 does not appear. Right, so it looks like a single phase calculation. Looks like a single phase calculation. There's an example in the text that you can apply that. Yeah, but just something to note. Okay, that's. Okay, so we'll do an example for a three-phase system. So it's a similar example to what we did before, but it's three-phase instead of single-phase. Yeah. Okay, so what do we do? Process. Pick a power base, right? that has to be common for the system. Typically, I will give you that, or the problem will define that, just because it's without the proper without a well-chosen power base, then the numbers don't make much sense anymore, right? Then you will end up with things that don't make too much sense, not very useful yet. But it's not wrong to choose any power base. And then you will pick a voltage base according to the line-to-line voltage that you have in the system. And then every time you see a transformer, so divide the circuit into zones by transformers. So every time you see a transformer, put a line, put a line, put a line, and define your zones. Right? So the zones are defined. So this is zone 1, zone 2, zone 3, zone 4. And then come up with the base values of, base voltages, base currents, base impedances in the different zones. Right? Now you've set up your problem. Then you need to draw your impedance diagram, or your impedance diagram is another fancy name for single phase equivalent circuit, per unit single phase equivalent circuit. So you take this, you draw your impedance diagram after that. You can draw the impedance diagram right now, right? So you can draw the impedance diagram, but you cannot put in values, right? So what does the impedance diagram for this look like? I have a voltage source. Maybe this generator, you will be given its impedance, right? And then I have a bus bar, and then I have what? Transmission line, and then I have a transformer, another transmission line, right? All of these are nothing but reactances, right? And then so on and so forth. Put 1, 2, 3, 4, 5, 6, and then the load will be 7. So then you have a load here. Maybe this is an RL or just an L, and then you close the circuit. So you've drawn your impedance diagram. This is your impedance diagram. Okay. Sometimes you can be given a load here. How would you do that? This load, maybe you have a load here. How do I put that here? Yeah, exactly. It's a parallel branch. Really, it's a 214 on steroids with some terminology. It's really it, yeah. Okay. So that's why power is easy. It's really 214. Okay, so here you're given this is an example with in 3-phase now. So here you have a 13.2 kV generator. You have these two transformers in the way and a transmission line in the middle, and you have a load similar to the previous example, but in 3-phase. Right? Exactly the same as the previous one, but with 3-phase. Yeah. So these are in actual values, also W instead of ohms. So. And then you write the name, the values, the rated values of the equipment. If you're given those values in the text, write them down, and then chop up the circuit into zones. So this will be one zone to the left of this transformer, one zone in this area, one zone to the right of this transformer. Right. So I have three zones as well. Also, the voltages, the ratings of transformers are different, and the power ratings are different, and the voltage ratings are different, right? So you will have to choose voltage bases properly so that you can eliminate these transformers, right? It's the same processing. And then they ask you to find the generator current, transmission line current, load current, and actual values, for example. Okay, that's what they're asking, and then the power of the load as well, right? So this is where this power. You will notice that the power will be, you will have to pay attention to the fact that the power per unit, the threes cancel away. Okay, so what do we do? As we said, chop up the circuit in 3 zones, right? Every transformer, sorry, this would have been aligned better with the transformer. So chop it up into 3 zones and define base values for voltages. Maybe you were not given a base value. They didn't tell us to choose anything specific base value somewhere. But here, in this case, they chose 13.8 to be the base value in zone 1. How do I choose the base value for voltage in zone 2? For you to eliminate the transformer, the ratio of the bases has to equal the ratio of the transformer terminal voltages. Okay, so V base 1 over V base 2 has to equal 13.2 over 132. Right? So choose one, and the other one will be defined. And same thing here. One is chosen already. So 138 divided by V base 3 will be 138 divided by 69. Of course, since 138 is 138, then 69 is what I get here. Yes, sir.
Don't we have to change delta y to something?
Good point. This we will do, I think, in the next. Is it say delta here? Yeah, it said delta y. Good point. So this is, since I didn't explain it yet, we don't, let's not go into that. So yes, delta y transformers are dealt with in a different way. Okay, so I will talk about that after we finish this example probably. Yeah. So I don't know if I'll get to it today or next class, but assume it's a star-star transformer for now. Okay, and in many cases I will actually tell you to ignore phase shifts. So very good point. So this delta y transformer means that the phase shift in the primary is not the same as the phase shift in the secondary. So you will end up with not a one-to-one transformer only. You will end up with a one-to-one phase shifting transformer. Remember, I alluded to that when we were initially talking about the transformer model, and we said that the ratio can be two numbers, or the ratio can be phase shifting as well. Why is it phase shifting? For this specific purpose? Yeah, but for the specific objective of selecting equipment rating, does phase shift matter? If I'm just working on, I want to select a cable for this transmission line. I want to select the cable for this transmission line. I don't care what the phase shifts of the voltages are. I just care about the ratings, right? So typically, actually, I will actually tell you to ignore phase shifts when we solve problems. But we will solve problems without ignoring phase shifts, so you see what the effect is. But when you're talking about equipment rating, I don't care. If I'm talking about designing of a protection system, I care, because the voltages, the angles between the voltages and currents are very important. Anytime instantaneously I have two voltages that are not in phase, current will flow between them. I mean, if I have two nodes with voltages that are exactly not in phase, then current will flow between the two nodes, right? So for protection purposes, I need to consider that, and I cannot put two transformers in parallel that have different phase shifts, because there will be circulating current between them, right? It's like two different voltage sources, right? So from a protection perspective, it's a good point. From a power rating perspective or power flow perspective, generally, okay, how much power is being consumed by the load from the generator? How much power is being processed by this transmission line? Is this transformer overrated? All of that, I don't care about phase shifts, but we will see how to deal with that. So good point. So for now, let's assume that these are two star-star transformers or delta-delta transformers, okay, that they're in phase. Now, divide them up into zones, and then calculate the base voltages. Everybody's okay with the calculation of the base voltages? Yes, ma'am.
Why is the first base voltage 13.8?
It's just a choice, because let's say we chose 138 here. Okay, let's say we start from here. I started from here. I chose this 69, and then I will choose this to be 138, and then okay, I cannot. This is 138. This is 132. So I have to choose a base value here, such that the ratio between them is the same as this ratio.
So you start from the right this time.
No, it doesn't matter. You can start in the middle. You will have homework problems where they tell you start in the middle. Okay, well, it does not matter, right? As long as when you go to the other side of the transformer, choose the ratio of the bases to be equal to the ratio of the terminal voltages. If you do that, then the per unit equations work with us, and they allow us to eliminate the transformer, because the impedances will be the same from both sides. Okay, so because also they ask us to calculate the actual values of currents and power and stuff, etc., then it's also good for you to calculate the base value for currents and the base value for impedances as well, right? So calculate the base values for currents and impedances, and just plug them, put them all in each one in its zone, and then draw the circuits and convert all values into per unit on the same base, right? So that's what they're going to do next. So they drew the circuit, and then they go through and convert all the values. Remember, this is a 13.2 kilovolt generator. The base voltage is 13.8. So to find the actual value for this voltage source, it's 13.2 over 13.8. That's the per unit value, right? Yeah, 13.2 over 13.8. The angle does not change. Remember, base values do not change the angle of the impedance. That's the same, right? We go through the same process we went through before. The same change of base equation that we used, because why do we use change of base equation here? Because the power base was chosen to be what? Power base was chosen to be 13 point, what? Not 13.2. What? 10 MVA. So this is the power base was chosen to be 10 MVA. So this transformer is the per unit value here was chosen using a different power base, right? So I have to do the change of base, right? For this one, it's the same power base, same voltage base. So as what I've chosen in a different zone. So I don't have to do anything. So you will find that this impedance 0.08 will just go down as 0.08, right? Same. But if not, if the voltage bases and the power base are not the same, you have to convert to the new power base. You have to apply the change of base equation. So any questions on this? Right, so I drew up the circuit, and now I have a simple circuit. I can find the current. Basically, it's the voltage divided by all the impedances that are in series. So find the current in per unit. That's what we have here. And then they ask you for the load, and then, since we have the current in per unit, I can calculate the load voltage in per unit, which is the current times the voltage, current times the impedance in per unit. And the power is the voltage times the current conjugate, right? There's no 3. There's no 3 anymore, right? Because the voltages and currents are in per unit. So, and then generator current in per unit is the same as the transmission line current in per unit, is the same as the load current in per unit. They're all the same in per unit, right? If they tell you actual values, then you have to multiply by the base value in the specific zone where the equipment is located. And here they convert back to actual values. So just by multiplying by the base in the specific zone, right? Just multiply by the base in the specific zone. Okay? Same for power. Okay, so another example. I have time. We can go through this. I mean, they're very similar, okay? It's same. Generator, 2 transformers, and a load. Okay. Determine the per unit equivalent circular supply system relative to 100 MVA base, the sending end voltage and power factor. So here they're asking you for the sending end voltage and power factor. So they're telling you that the receiving end, which is my load, then it's a circuits problem now in this case, like chapter 2, right? What we've done now is reduced this chapter 3, which is a bigger power system with transformer ratings and stuff. We've reduced it to what we have in chapter 2. So now they go back and complicate, add sort of same complications that we had in chapter 2, draw power triangles, look at power factors and stuff like that. So the previous examples didn't have anything like that, but here they start and tell you that my load is 40 MVA, 0.8 power factor lagging. And they are asking you for what voltage is at the sending end, and what power factor is the generator operating at, right? So it's basically what like 214 in chapter 2 material, right? Chapter 2 material applied to the power systems. Okay, so it's required they want to maintain 30 kilovolts at the load. So they're telling you that I want to maintain 30 kilovolts. Typically, that's what you have to do. Maintain voltage at the load. Make sure that you're able to satisfy the load's power requirements. This is where you typically start. And then the utility figures out how to control its generators and transformers, right? That's how it works, yeah. So they told us to choose 100 MVA as the base power for the system, right? And then they told us that we want to maintain 30 kilovolts at the load with a certain power factor. Now we do what? Draw the circuit, chop it up into zones, and select voltage bases in the different zones. They didn't tell us, they didn't restrict us to a certain voltage base in a certain zone, so it's really up to you in this case. So what is a good choice? Does not matter. I mean, you can choose it to be 30 kilovolts, and hence in that case the receiving end voltage is 1 per unit, because they want to maintain the receiving end voltage as 30 kilovolts, right? So you can choose 30 kilovolts as your voltage, line-to-line voltage base in zone 3, for example. And in that case, everything, the receiving end, this is going to be 1 per unit, angle 0, your reference, right? And then you can see what happens before that based on the impedances that you have in the circuit. And then you have to choose the bases in the other zones, maintaining the ratio of bases to equal to the ratio of the transformer terminal voltages, right? But I don't know which one they chose. Let's see what they chose. Okay. Okay. Blah 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 blah. Okay, let's see. Transmission line impedance in per unit. So they tried to find the transmission line impedance in per unit. This was given as J80. So they I didn't include the part where they chose the base voltages. So the different zoning up the circuit and stuff like that, I didn't clearly show it here. But if I here I'm choosing the transmission line impedance is equal to, in per unit, is equal to actual over base. Base where? In that zone, right? So we obviously chose base voltage in the zone of the transmission line to be 132 kilovolts, right? So here, zone 2, I want to call it zone 2. I would do this. This is zone 1, zone 2, zone 3, right? V base 2 will be 132 kV. V base 3 is, V base 1 is. So this is 132. So then it's easy to say this is 33 because the transformer happens to be 132 to 33 as well. How about here? V base 1. This is 132 and this is 11. So it's at 132, 11 kilovolt transformer. So then the base 1 here is 11 kilovolts. So base voltages selected, right? Base, then you can go, I would go ahead and write, base, at least for practice now at the beginning, write, calculate your current base. Your power base is 100 MVA. So S base is 100 MVA. This is your power base. S base. So you should be able to calculate from S base is equal to voltage base times the current base. You should be able to calculate the current base in zone 1. Impedance base in zone 1. Then current base, zone 2. Impedance base, zone 2. Do the same thing for zone 3. And now, go and calculate your impedances in the different zones. So they started with the transmission line impedance. This was given as an actual value, J80. So per unit transmission line impedance is equal to the J80 divided by the base value of impedance in that zone. Right? So base value of impedance, it's S squared or V squared over S or something like that, right? So calculated the transmission line impedance in that specific zone using the old value and the base value of power and the base value of voltage in that specific zone. And then the same thing for the transformer, 2 transformer impedances and the power. So I think you can go through this one. Go through this example. We'll stop here. So this example is very similar to what we did. So please go through this example. The only difference is they ask you, okay, what's the power factor of the generator? So please go through this example yourself, okay? And then next class we'll look at what was alluded to earlier about the star delta and how that affects phase shifts, okay? So please go through this example yourself, please. The homework has been posted and it's really what we've discussed today.